Physics, Consciousness and Reality, Dickie Dredd, Nigel Adams. Most of us assume that the world is made of solid things, sitting in definite places, whether we look or not. But that starts to break down when you look closer. At the smallest scale, things aren't solid. They're not fixed. They're not even fully real until they're measured. So, before we go further, if reality isn't definite until you observe it, what is it doing before that? This is part 7 in the video series of, and we're still on chapter 1, The Hard Science. Section 4 in the book, Quantum Mechanics, The Strangeness of the Small. If relativity wrote our ideas about space and time, quantum mechanics tore up the script about how matter behaves. It's a theory of the very small, particles, atoms, the building blocks of everything. And it's a world that doesn't play by the rules we take for granted. The first shocker is wave-particle duality. In our everyday world, things are either solid objects or flowing waves. A football is a particle, a ripple on a pond is a wave. But in the quantum world, everything appears to have both properties. Light can act like a wave, spreading out and interfering with itself, but it can also show up as a particle, a photon, a single packet of energy. Same goes for electrons, which we normally think of as tiny specks of matter. Under the right conditions, they appear to spread out like a wave. Which one you get depends on how you look at it. That brings us to the famous observer effect. In quantum mechanics, particles don't have definite properties until they're measured. Before you look, an electron isn't here or there. It exists in a superposition, a cloud of possibilities. Once observed, the cloud collapses into one outcome. And there's a bit more on that in the next section. Schrödinger's cat, the thought experiment you've probably heard of, takes this to an extreme, until you check the cat is both alive and dead. Sounds absurd, but it's how the maths works, and experiments back it up. Note that the cat thought experiment was first written about to show that superposition must be nonsense, but there are many variations, often involving complex networks of observers, so it wasn't written to show quantum mechanics is true, it was written to show that it must be nonsense. Then there's entanglement, which Einstein famously called spooky action at a distance. Take two particles that interact in a certain way, and they become linked. Separate them by a millimetre or by a galaxy, and they remain connected. Measure one and you instantly know something about the other, no matter how far apart they are. Looks like information is jumping faster than light, which seems to break relativity. Yet experiments keep confirming it. We don't fully understand how, but the effect is real and leads to the idea of teleportation, and single photons have actually been teleported. They're not quite ready to beam anyone up yet. But it is worth clearing up a common misunderstanding. Quantum entanglement does not mean that any two particles in the universe are mysteriously connected, or that everything's connected. For entanglement to occur, the particles first have to share a history. They must interact in such a way that their properties become what's called correlated. Now I'll just pause to explain what correlation is. So correlation refers to a statistical relationship between two variables, where the state of a value of one is linked to that of the other. In this context, it means the particle's properties are connected, such that measuring one gives information about the other. And it's only in that situation, it's not everything's connected, man. Only then do measurements on one have a predictable relationship to measurements on the other, no matter how far apart they later travel. Without that prior correlation, there is no entanglement. This is very different from the mystical idea that everything is connected to everything else. Quantum mechanics does suggest a universe full of surprising correlations, but it does not give license to say that your thoughts influence distant galaxies or that crystals communicate with each other through quantum links. Entanglement is powerful, strange and real, but it is also precise. It applies only to systems that are prepared together and measured under very specific conditions. In this context, correlation means that the outcomes of measurements on two particles are linked in a way that can't be explained by random chance. Imagine you have a pair of gloves, one left, one right, and you put each into a sealed box. You send one box to London and the other to New York. When someone in New York opens the box and finds the right glove, they instantly know the London box contains the left one. That's correlation. With quantum particles it's stranger, because until you actually open the box by making a measurement, neither glove has a definite hand in this. The outcomes exist only as probabilities. But when you do measure, the results are still linked in a predictable manner. This doesn't mean the gloves are sending messages faster than light, or that every object in the universe is tied together. It simply means that when particles are prepared together in a special way, their properties remain correlated no matter how far they are later separated, what physicists call non-local effects. And here's the crucial twist. Unlike the gloves, the properties of quantum particles are not fixed in advance. The act of measurement helps bring them into being. That is what makes entanglement truly weird. Quantum mechanics is deeply probabilistic. In classical physics, if you know the starting conditions, position, speed, direction, you can predict the future exactly. Not so in quantum world. Here, the best we can do is calculate probabilities. This isn't just about ignorance, it's baked into the universe. Nature itself rolls the dice, or so it seems, contrary to Einstein's grumble that God does not play with dice with the universe. Out of all this strangeness, physicists have built quantum field theory, the framework that underpins the Standard Model, and we'll cover that later. This describes how particles and forces interact with astonishing accuracy. The quantum world may seem alien, but it's the reason your phone works and why we can map the brain. Yet for all its success, quantum mechanics leaves us scratching our heads. What does it mean that observation shapes reality? Is consciousness involved in collapsing the wave function, or is it just a feature of measurement itself? Why does entanglement work across vast distances? And why does the quantum world, so strange at the micro level, give rise to the familiar solidity of the macro world we live in? Like relativity, quantum mechanics shows us that our everyday assumptions are fragile. Objects aren't solid billiard balls. Reality isn't fixed until it's observed. And cause and effect don't always behave the way we expect. If relativity stretched our imagination, quantum mechanics smashed it to pieces. It tells us that the universe, at its core, is not certain, not definite, not shimmering with but shimmering with possibilities. And maybe, just maybe, that's where consciousness sneaks back into the picture. That's not an assertion, that's just a thought. It is here, though, that we need to tread carefully. Many folk who do not really understand quantum mechanics have jumped on the bandwagon and use it to explain all sorts of odd stuff. That's not what we're going to do here at all. So don't believe all you're told about quantum mechanics leading straight to magic, etc. That's often not backed up with any evidence. Correlation refers to us... okay, yeah, I've said that now. Okay. So, what this section is really doing is showing that at the most fundamental level, reality is not fixed but probabilistic and dependent on interaction. And if that's true, then the universe isn't a collection of solid objects, but a field of possibilities waiting to resolve. Because the real problem may not be how particles behave, but what it means to observe anything at all. So if this isn't what we thought, what exactly turns possibility into reality? Next up, we're still on chapter 1, the hard sciences, but we'll move to another part about quantum mechanics, which is section 5, wave function collapse, randomness, models and interpretations. So thank you. The book still working on the cover for the book, but should be out very soon. I'm getting some help from my good friend Paul Garber. And so that should be out any day now, hopefully.